go. Hello people, this is an introduction to Rust with Tim McNamara. Thank you.
Hey, thanks very much. We've actually had some very people generously donate their time. William and Josh here are already proficient Rust users, and if you have any queries or concerns that I can't address, feel free to wave, and I'll try to direct one of them to you. And do make use of that facility, because I will make mistakes, and it's always very, very difficult to know. There's so many ways to make an error, and I can only direct one way fix one thing at a time. So, welcome. The first thing to say is the role of today's session is to really give you the confidence to make your way through the journey of learning Rust. I'm not going to be able to do it all in 90 minutes. I can't teach you the whole language. It's big, it's complex, it's kind of scary. But what I can do is let you know that actually you're totally welcome, and your questions are extremely valid. So hi, kia ora tātou, ko remutaka te maunga, ko kairanga te awa, no whakatiki au ahau, ko McNamara toko whānau, ko Tim toka inoa. Remutaka is my mountain, the Hutt River is my river, Upper Hutt is where I'm from, my family name is McNamara, and I'm Tim. I just want to make 2 acknowledgements. Today we meet on the traditional lands of the Gimbe people, and I pay respects to elders past, present, and leaders emerging. Also, thank you very much for Canonical. I'm actually here under their dime, which is really, really generous of them. Here's the big outline. What we're going to do is try to switch between some theoretical material. You guys can sit down, by the way. Don't feel like you need to. Maybe, Josh, if you could go to the other side of the room. The slides are not yet online because I've just finished them, right? Yeah, that's right. Yeah. So what we're going to be doing is spending a little bit of time I'm going to try to give you some tips that helped me as a Python developer kind of understand the Rust way. And we're going to alternate between theoretical material and practical material. So the first section is, don't fear the compiler. Has anyone never used a compiler? Cool. That's perfect. So, we can't run things directly. We need to, quote, compile them. But it's actually not so difficult. It's very much like running your tests. There are 2 ways around this, actually, and one of them is right in front of you. If you're on Linux, you can, the recommended method to install Rust is to visit a web page, which is just here. You can do some other things too. So kind of pick your tool of choice. If you're on another platform like macOS or Windows, feel free to go to rustup.rs. Down the bottom, there is a actually, let's go there and find out. So we'll be given these instructions, and then we can kind of click on other installation options. And hopefully that's perfect for you. If you do have any trouble, you're more than welcome to ask any questions on the forum. So right now, the main thing that you need to be aware of is this one here. I'm just going to keep going. If you have any problems, please raise your hand, and I'll kind of sick one of the gents onto you. Oh, that's the wrong thing. So the first thing we need is to know about Rust C. So this is the Rust compiler. Pedantic yet polite. So what we're doing here, just to give you very, very brief instructions as to what's actually happening. We've got some Rust code that we're catting into a file in our temp directory. We run the Rust compiler, and then we have an executable that prints out hello LCA. So what the compiler is doing is taking source code, translating it into something that's executable, and then you can run it. But actually, we don't interact with Rust C very much directly as Rust developers. We interact with a tool called Cargo. So I would recommend that once you've got Rust installed, to try out these sort of 4 commands. So inside a temp directory, we run, Cargo would have come as part of the installation if you had used that recommended installation method. And for the curious who don't want to do it themselves, I'll just do it for them. I'll try to avoid tmux. So here we go. What did I say to do? I said cargo init -- vcs none, which isn't necessary, but I don't really need a Git repository for this. And I'm just going to call my project hello, but I think, bang, I've got a folder there. I can cd and tree recursive. There. There's what? What did I do wrong? Sorry? Yeah, well, here. There we go. So now I just need to do cargo run. All of this stuff here is, helpful, but I'm not very interested in that. So I can set it to run quietly. It will just run the executable. So I'll go back to the talk. So we were here. Is there anyone who hasn't received hello world from their compiler? That's very good. That's 100% so far. We're all doing well. And now the other option is, but actually, if you're from, you've done your PHP scripting or you have only used JavaScript and so forth, a compiler can still feel kind of strange. And installing toolchains and so forth is kind of annoying. So one of the options that you've got is to learn Rust without installing anything. And so if you can visit play.rust-lang.org, Mozilla kindly provides the resources to be able to compile the code in the cloud and present you with the results. For people who prefer to have things self-hosted, it's open source, you can go and install it yourself. There's actually also a REPL. Don't know, so this EVCXR stands apparently for Execution Context for Rust. And we can actually, so this is me defining a function, like inside the presentation, and I'll call it. And I'll just change it just for special effects. If anyone has used, as from the Python data science world, the Jupyter Notebook is a really, really familiar environment. And Jupyter provides the ability to install separate kernels, which enables other programming languages to be supported within the Jupyter Notebook. And I apologize for the font size.
What program are you interacting with?
Right. So what is this? This is craziness. We are compiling on my laptop. This is compiling a new rand function. It will create a temp directory, create a new cargo project, insert the source code, compile it, and then execute what I've done in the cell, and then present the output.
So is this the Jupyter software running on the machine?
Yes, it is. Yep, so everything's running locally. Please don't somehow find your way into the network onto my machine. And I can change whatever I want, And we'll actually get a better implementation of random number generation pretty soon. But yeah, this is going to allow us to play interactively without needing to learn all about the compiler straight away. So now that you've got Rust installed, you're having Cargo installed. And if you've got Cargo installed, you can install other tools. And the tool that I am playing with right now is called EVCXR. And underscore REPL is just a sub package or subcrate, which provides you an executable that looks sort of slightly like a Python script. You can play with that interactively on the console without needing the overhead of dealing with the compiler. It deals with it itself. And this Jupyter thing is really similar. Like I'm running an Ubuntu system, and so for me, I can just sudo apt install the Jupyter notebook. Then I can run cargo install evcxr underscore Jupyter, and then it creates an executable which I then install. So those three commands are what have enabled this.
So Jupyter seems to install a lot of Python stuff.
Yeah, Jupyter is a very dependency-heavy kind of system. It's going to, yeah, so the Jupyter side of things is you have it's all based on, your browser doesn't actually execute anything. It's sending messages to a sub-process, which itself spawns sub-process to run what you're doing. And there is actually, so I'm just going to kind of push through slightly unless, do we have any questions here? Cool. To speed things up, you want a cache. This is a really, really useful thing to add to your workflow. SCCache basically speeds up the compilation of one of the projects that you'll be working on by 5 times on my machine. And so that, yeah, is cargo install SCCache. And to use it, we provide the part. I would recommend putting that on like bash aliases or bash RC or so forth. Rather than, providing this at the command line every time. But so if we've got this Rust-C wrapper thing, it will speed things up for you. Okay, so now we've done all the setup. Is everyone, we're smiling now? We're happy, we've got Rust installed, we have got Cargo installed. Let's learn some Rustisms for people that have never dealt with Rust.
We don't need to do it. Basically, the slides are going faster than we can load.
I think we've had a few people come in since you started.
Right, ooh. Who here does not have Rust installed that wants it installed? We've got 1 over here and 2. William, do you mind going to the back? There's a gentleman to the right.
Is there anyone who's just Rust and Cargo and Jupyter? Was that it?
Yeah, that's the core stuff. There we are. Yeah, just here. Okay. The first thing that I found really difficult to handle was that when you enter into the Rust community, suddenly you're throwing a whole lot of jargon that you've never encountered before. And my recommendation to you would be to just kind of breathe and pass through it and like kind of push through, because none of it is essential for what you're trying to do. And as you gain familiarity with the language, these terms will start to become more and more interesting. So to start off though with the code, one of the important things is that Rust is immutable by default. So I've defined this variable here, A. I've been given it a type annotation, which is a 32-bit integer. So this is a Java int, basically, I think. But if I try and mutate it or change its value, like Rust is going to complain. Rust, one of the Rustisms is that everything is safe by default. And so a safer default from read-write access is read-only access. So one of their lessons is that Rust will always default to the safest case. Rust has a very strong opinion about types. And I have skipped something. Oh, yeah, right. So excuse me, it's not going. Why not? So we can add numbers, right? We've done this a few times already. But we can't add a floating point number to an integer, which if you have used a statically, can I just get a sense in the room? Like if you've used Python like I did, like does this seem like something that's useful or not useful? There's bound to be people who find this super useful. I still find it kind of super frustrating. This is one of the culture shock things that you need to kind of accept as someone who's coming from a dynamic programming background, that the types that you provide are going to be the types that the compiler plays with. If you would like them to be coerced, you need to do that coercion yourself. That includes even integer types. So integer literals can be given a suffix, which declares which type of integer it is. And Rust will refuse to, even though this is a perfectly valid thing for integers to do. It wants you to tell it whether or not it should convert the I32 to an I8, or if it should convert the I8 and promote it up to an I32.
I'm trying to type some of this into the Rust command, Rust lines play.
Okay.
And
Right, okay. So the question is,
you've been typing out this.
all right, so let's, so the question is, like, hey man, stop. I'm trying to actually do this. So I will, at the moment we're just kind of we're going through a bit of a demo. The play mode will have, it has some opinions about how to do things. In particular, it always will want a main function. Oh, again, I apologize for the size. So this is exactly the same thing that we saw. We're going to get this execution context, and then this will be the same error message. You know, here I thought that you were going to give me an I32, but I've got an I8. So in order to execute anything inside the playground, it needs to be kind of wrapped with inside a main function. Okay, I'm going to go back to my slides. We've got like this whole zoo of numeric types. If they mean very little to you, iSize and usize are the ones that actually are the integer type that your CPU uses natively. So the size here denotes the width of a pointer in the CPU on your computer. Everything else, well, yeah. Actually, this is wrong, so I'll just change that. Sorry, excuse me. We also have 30 to 64-bit floats as well. So this is a bit weird. I'll change that so that it's a bit different. We can give any type methods. And in fact, you're able to add definition. You're actually able to impute, or sorry, wrong word. You're able to give types that are defined elsewhere, kind of new magic. You can give them methods through a some functionality that we're going to call traits later on. Again, so this will feel syntactically very strange. I think I can do this. That might complain. All right. Yeah, so I'm adding the extra brackets there so that it knows how to tokenize things. And it's saying, look, you've given me this generic float, but I need it to be a specific floating point type. And now that I can understand exactly what type you're dealing with, I'm able to compile it. That's strange. I wonder why I did that. So let's find out what floating point numbers can do. So we can go to the Rust documentation, which is at doc.rustlang.org. And if I try F32, so we want to take so confusingly, there we've got this problem where F32 is defined in 3 places. We've got this primitive type thing, I don't know what that means. It's in standard and it's in core. I'm just going to click on the first one. It will give me the methods that have been defined for that type. And I wanted to take POW. So here we go. Actually, the problem was that I wasn't specific enough. It wants to know if it should be raised to an integer or to a floating point number, and they are different methods. So I can kind of go back. If I change that to power I should get 3 to the power of 4. If I go to floating point literal, I get kind of the same thing. We've sort of touched on this first. Rust is always going to prefer safety. So there are cases when it's going to be exceptionally pedantic with your code. And you're going to struggle and you're going to be frustrated because you're like, buddy, just let me compile this thing. I know what I'm doing. I've been in software for a while. And the compiler is going to gently say, sorry, sir. It's possible, mathematically, that you're wrong. And you'll just have to kind of live with that. I apologize. I'm just going to pull this up into the top cell. And so there's actually a lot of, one of the things I want to get across is that Rust is an exceptionally well-designed piece of software. It has very robust software engineering principles behind it. And except,
Why is this printing 4?
Why?
Why is this printing 4 here after that if statement?
Right. So there's a really interesting question. I believe it's on the next slide, but we'll carry it here. So what we're doing, if anyone's used Python, they should not expect flow control to return a value. This kind of seems utterly bizarre. In Rust, basically almost everything returns a value. And so every block will evaluate to a value. And therefore, we can do some shorthand, I can actually assign. Now, it will complain about types, I believe, and I will probably need a semicolon in there. But the answer is that Rust is an expression-based language, and it's much more creative. Well, it looks really odd to someone who's from a non-functional background. Rust is this really strange mix of ML and something C++ or Java-y. And so there are influences from both sides of if you've ever used Haskell or Java, you kind of might find a happy medium with Rust. And so, but if you've used Ruby or other expression-based languages, you might feel more comfortable here too. Oh, here we go. Even things that don't return a value return a value. That value is known as unit, and it evaluates to the unit type, which evaluates your unit. So here we go. Oh, we just did that. We just did that. And then the next one will be asking us what. So then, like, what is the value of what? It's 4. And we can match what. So match is like a switch statement. We know that what is 4, and we have this kind of nice syntax for saying that when the value, this syntax is saying, like, here are my list of predicates. Once you match one of them, give me the result on the other side.
Going back, the if statement has to have an else. You can't have a.
No, it doesn't. It is telling us that, so the compiler is saying that you haven't provided.
Just go back to the if statement and you put a semicolon on that 4.
Yeah, right.
Semicolon on 3.
Yeah,
Delete the let.
yeah. Okay. So if they evaluate to the same type, it's okay. So if there's no else, putting a semicolon here changes the expression from returning an integer. So there we are returning an integer, and now we're returning unit. So the semicolon is changing things. And again, this is going to be one of the things that will feel odd when we start looking at functions. And
Consider it in a different way. The lack of a semicolon means a return statement is implied. So the semicolon here prevents the return of 3, which means that as there's nothing else subsequent, the compiler is inferring that a unit must be after the semicolon and it returns it. When the semicolon is removed, there's an implied return and the 3 is returned. Of course, now that 3 is being returned, the other option, whereas 1 is equal to 2, which I don't know what world that would be, but the other case now no longer has a return. The types don't match. So anything you would assign out of that has a problem. So this is where flow control gets a little bit different in that it's the lack of a semicolon means return, and if you add the semicolon, you're terminating so that there's no return there.
yeah.
Does that help?
Yes, it does. But does that mean I should always just put a semicolon no matter what?
While you're getting started, it might make more sense. So if when you're getting started, feel free to write unidiomatic Rust code.
There is a return keyword.
That's right. We can add a return, which again is considered non-idiomatic, because we know the last, and a block will evaluate to the result of the last expression. But we can use the return keyword plus an expression plus a semicolon to kind of get the behavior that we would expect from explicit, from like the Python idiom of explicit is better than implicit, for example.
Have you done much C?
Yeah.
Like in C, you put a semicolon there by default. So treat this as like an extra feature where if you leave off the semicolon, now it's being treated as an expression instead of a statement.
Right. So this is another implementation of a random number generator.
Don't roll your own crypto.
This is not. This is published. This is published and verified. As long as the seed, yeah. So, and so it's just a whole bunch of, it's kind of washing out bits around. And it turns out that this is it's not cryptographically secure, but for stats, which is this, Margisella is a statistician, the speed boost you get from just using these primitive operations is really quite good. So what the problem that we've got here as someone who's new to Rust is that it's very strange to us that just adding X by itself returns X. So a more natural thing while we're getting used to Rust, is to add an explicit return as long as we also include the semicolon afterwards. Let's try and find out. It probably does. Okay, so this is still fine because it's here. But if we were to like force a return, yeah, that's right. So because it's right at the end, there's almost no benefit. That means return.
So the return expression returns.
Yeah, right. So that's kind of mind-bending. So what's actually happening is that return is being evaluated, which itself returns an X, but that's kind of fun. Whereas this return is an X. Anyway. I had never played with generics when I was a Python developer. I mean, I'd been a Python developer for over a decade. And I was just like, what is this craziness? When you define data types, you can also provide type parameters, which then kind of get filled in by the compiler itself. And we can parameterize the types. So for example, I could say that I would only like to be able to accept types in my new type that can perform mathematical operations or look like floating point numbers. But I don't care if it's a float 32 or a float 64. And then the compiler takes the time to consider every case in which your data type is used and will write out the binary code to be able to, it just duplicates everything. This is one of those terms that we encountered early on, is used really heavily in the documentation. It's called monomorphisation, which means that we can, yeah, which is why I tried to avoid it. So here are two terms that are really, really scary. And they're not, says someone who knows about Rust. My own personal view is ownership is a really, really bad name for anyone from like the Western tradition because it implies property, but property rights have nothing to do with borrowing in Rust. The owner of a value has the responsibility for destroying the value when they go out of scope. That's all an owner does. That's the only thing it is responsible for. If I were to think of my own personal property, I could exclude everyone else in this room from accessing my property. An owner cannot do that in Rust. And so borrow, I like to just think of as read-only access, and mutable borrow as read-write access. Okay, so we're going to take a very large tangent from Rust very, very quickly. In our tutorial, we're actually going to be implementing an LSystem Interpreter. So that implies we need to know about what LSystems are. And I will change that. They're a formalism. So it's a string rewriting tool which basically encodes movement. So here we have F standing for forward and plus meaning turn right. And we can create a square with the string, as long as we've got something that can interpret it and draw pictures. So by the end of the tutorial, we have an initial state, which is called the axiom for whatever reason, and a rewrite rule, which is whenever I encounter an F, replace it with the rule, and successive iterations create more complex patterns. We can also do some really, really fun stuff, like create like the Hilbert curves. And we're also going to be able to introduce stack and create procedurally generated plants. So that's our goal. There's heaps more to them, and there's a really nice book, actually, called The Algorithmic Beauty of Plants, that you're more than welcome to kind of introspect. Now we're going to kind of break out from the presentation and break open some code. If you have cloned the repository, this will already be in your like local directory.
The URL to the GitHub repo wasn't on the page that you pointed to.
Yeah, because the GitHub repository is like 2 hours old. So the GitHub repository, github.com rust-in-action is the org, and the only repository in there is Intro to Rust tutorial. Oh, 7 hours. It feels like 2 hours. Okay, so we've got a couple of implementations of this LSystem Interpreter. I am just going to start from scratch, I think. Why is that stupid? That's really odd. Just going to create a new window and start again. So, inside this thing are a couple of implementations, and inside each one will be, if we ignore Git, so this is what we're looking for. Each one has full files. So we were interested in LSystem's easy. And this one is going to be, so we've got this cargo.toml thing. Cargo.toml is some metadata about our project. And we define a dependency, this turtle thing. That's kind of the important line. Right now, I can just do cargo build. Actually, we'll do cargo run because it's more fun. Now, we're slamming the Wi-Fi. That's OK. So it's going to kind of go crazy for a little while. Actually, maybe I didn't want to do that. Do very intensive programs. So yeah, Rust tends to be, as a community, quite a dependency-heavy thing. They tend to be relatively small dependencies, like, but there's a lot of them. C-line's probably the wrong thing, but. Has anyone built the square? Has anyone gone faster than me? Oh, cheating. Oh, right, OK. That's a fair question. So the question was, how does the repository name map to the project, I believe? The projects are actually subdirectories of the repository. So the commands that I executed, so I did cd temp, and then I ran git clone. And then I moved into, yep. And in here, I've got, I guess, 5 implementations of this interpreter. And the one that I'm interested in now is LSystem's easy.
Yeah, but I guess I'm asking with regards to the cargo.toml, and then you have a dependency there called turtle. So, I mean,
There's a website called cracks.io, and that has
Right.
a singular name for that dependency, and then that has the mapping to GitHub repository. So cracks.io is the source of these.
Yeah, so cargo will know. We don't, cargo will know how to find turtle and find its dependencies using a facility called crates.io. That's been pretty heavily exercised. So there are two commands that are interesting. One is cargo build. And I'll just add the quiet flag. This should be quite quick because I've already built it. And the other one is cargo run. And so this should be appearing on your screen once it's built. And I'm just going to look through the code really easy. So I'm going to go into source, main.rs. Has anyone here? Oh, there's a question at the back. Yeah, potentially. Yeah, hopefully Willie can help you out with the compiling. Has anyone used Logo before? Right. So we're just using Logo commands here. This is we're initializing this turtle thing, calling it Fred. We need to define Fred as mutable, otherwise we won't be able to move. And we just executed commands, so we're just building the square. Hopefully that's relatively straightforward. The Interpreter 0 project is a little bit more interesting because it actually interprets the pattern that we've generated. So you'll see that Rust uses string literals and in two different forms. So here we've got double quotes, creates a string. Single quotes are a different type. They're characters. We can do the same thing in Interpreter 2. So cargo run should get a very similar result. Happy to answer any questions from the field. Yeah, sure. I should do it myself. So I'll just find it. It's all the way back here. So to start with, to add this cache, if you're running Linux, we can export Rust C wrapper and which SCCache is going to just be something pretty easy. And then if we cargo run, it should be much, much faster.
And then I'm joking about the density, like it's only SCCache, it's like 279 crates.
Yeah, that's crazy.
Yeah.
Oh, there was a question over here also.
For the match statement, types just need to implement like equal crate, that's it? Or
Yeah. Okay, so this is pretty basic as well. We're just creating a circle. We're going to be adding some complexity shortly. But hopefully this gives us an idea about the workflow. We write our source code, we can compile it, and we've got a couple of options for being able to use this in a sort of a more we've kind of got through like REPL type things as well. Just going to go through. Here we are. We're just going to we're going to add some stuff to our toolbox. We can't really write much Rust right now. All we've got is numbers and match statements and if statements. Well, match expressions, but we need to actually define some data types. We kind of got two main ones plus a hidden option that is there behind the scenes. Struct is Rust's workhorse. It's where you'll probably go first, if you have ever defined a class before, you've defined a struct. We started off with the struct keyword. We can provide fields with types. There's no constructor by default, so there is a literal syntax that is supported sort of out of the box to get you off the ground. And this is going to complain because it doesn't know how to, it's going to say that it doesn't have display or debug. It can't be formatted as a string. It doesn't know, Rust doesn't know how to convert .2d to a string. So we're going to ask it to derive, like automatically give it the methods to be able to display it as a string. And there are a few things that we can derive quite easily for basic types. By default, Rust isn't, your structs are going to be very, very isolated from the world. They don't have the ability to, they don't have equality. But we can effectively ask the Rust compiler to write the code to give it equality and to give it multiplication if we wanted. By default, so, well, not by default, with these derived statements. Whereas, just in case you're curious, you'll probably see partial equality or partial EQ more commonly than EQ. Floating point numbers are only defined as partial EQ, and so it's actually the primary trait for equality testing. It's where the because not a number does not equal not a number. And so if you look into the depths of the Rust source code, EQ does not actually do anything. There's no added benefit apart from the fact that it provides a little bit, you can parameterize those generics on the basis of it, but it doesn't actually add any. There is sort of this inline syntax if we don't want named fields. And so I've got this kind of color, which is, mid-gray. And I'll just show you how to access one of the fields, because we don't have a name. But we'd like to know, let's say it's H value. Which is very, very familiar. Like, it looks very, very similar to tuples in Rust. We can kind of create like these anonymous types. And this here is a collection of 3 other types. We've got an integer in here and 2 floating point values, kind of this random mishmash. And that's going to satisfy the compiler. Oh, we may as well evaluate that. Just kind of get our 2 out. Oh, are you sure? Oh, right. I changed the name. Now, the reason why tuples are important to mention is that they're actually there and present without you even realizing it. So you'll see them as the return, or even as the return value of functions. We can take a tuple and destructure it into separate variables if we want to. And, here's the question, like, where is the tuple here? We haven't defined a type, but it's there. This thing is an array. Oh, this things array is an array. The tuple actually turns up here. This isn't, it's markdown, so. There's one, so we've got structs, we've got tuples. There's one kind of other thing that we want in our toolbox. It's enums. And they're significantly more common in Rust than other languages. They provide very, very efficient and type-safe matching. And they're really powerful because we can actually add data into our variants as well. So that this action thing, let's imagine we're one of these turtles scrolling around the screen. We can move forward, we can move back, we can turn. We can, in a type-safe way, provide the ability for the programmer. I know this is a horrible API, but in either radians or degrees, for example. And so we kind of have an enum that embeds an enum. And every single permutation, whenever Rust sees an action in source code, it will require you to deal with every single possible case. So you will have no edge cases in your source code because Rust will refuse to compile if they're present. This is the primary thing that using enums effectively was kind of one of the biggest mental shifts from a Python-based language, because I was so used to just taking JSON files, turning into a dictionary with string keys, and I was done. But Rust really encourages you to take your messy, dirty input data, convert it to something that is type safe and secure, and then use that internally. At least that's my impression. Does that kind of echo other people's views? Yes, I got a nod. Okay, we've actually gone through 0. So I'm just going to blow through collections as well. There are 3, so in terms of things that are confusing to newcomers, the fact that we have 3 things that seem to hold lots of stuff makes it very, very difficult to intuitively know where to go first. And my recommendation would be to start with vector, basically, until it doesn't suit your needs. We can do some useful things with Vex. I'm just going to pop out, and this is not a, just going to add a code cell so that I can play with this a bit more. And let's pull this over here. Jupyter Notebooks is super cool, by the way. So now I've got this V thing. So there's nothing in there. It's an empty list. But it's going to stay an empty list because it's not mutable. I can append to the list. What are some other useful things to be able to do with a collection of stuff? Pop, we can pop values. I will just show you iteration. Yeah, well, let's do pop and shift, because that's fun.
So a question about immutability. So are you creating new arrays every time you do a push?
No, okay, right. So there's a really interesting question. No, you are not creating. So to start off with, when I call vec new, I get a 0-sized vector. And then in order to push, my program needs to ask the operating system for some memory. And it does that, but at the surface, nothing has changed. The mechanics of vector take care of the allocation and deallocation of memory. Inside vector are 3 fields. We've got a length. We've got a, oh, that's not going to evaluate. We've got a capacity. Awesome. And we also have a pointer to the actual array that we've stored, or that is being managed on our behalf.
So vectors by default cannot contain multiple types in one instance.
That's correct. The question was, you know, this looks useful except for the fact that what if I want an integer and a string? Yeah, and then the answer is you pack it in an enum. So like my stupid type, like we could, yeah. So what we would do is, let's say that we have input, user input, and we've got height, because height's so useful. And we've got a string, because they might just give us a free text message. And so now I can have a vector of user input, but here in the height, oh sorry, here when I start to push my integer in, I actually need to tell it that the height is 1 of whatever unit we're dealing with. So this is the way to create effectively an instance of this enum.
So does vector actually contain just a pointer to that enum in that case?
No, it will allocate the, no, an enum, there are no references in here. Actually, the string does have a pointer to something else, but Rust will pack all of the user inputs in a single array. Until you reach the capacity of that array, it will then allocate another array that's twice the size, push all the stuff, copy it all across, and then kind of append the other data.
The enum is effectively a number and a field to store data.
Yeah.
And the number represents which instance it is.
Yeah. If you're from a C background, an enum is a typed union, or tagged union, sorry. Enums, vectors, sorry, enums, tuples, and one other type are all, and structs are all implemented effectively as C structs under the hood. So now I get this really confusing terminology. Everything that Rust does is type safe, and it needs to know the size of everything that it compiles, otherwise it's not type safe. But there's also a term, an unsized type, that you'll encounter. What this is saying, effectively, you know, for anyone, I'll start with the people that know what I'm talking about. If you've got a pointer to some stream of input data or an array that you've been given from the outside world, you don't know how long it is. And we refer to this, but we know the width of the pointer, and so Rust is satisfied by knowing how much memory to allocate when we've got multiple slices, but it will still refer to the type as unsized. We take a slice, which is effectively a reference to an array or a vector. We can take slices of other collections of things ourselves once we've got to borrow to that object, but we'll see that not here. There's one other kind of collection type, which is not, with vectors, we're able to kind of expand them and contract them at will. Arrays are fixed, but they're often the kind of the bedrock of, well, the most primitive collection type that everything else is built from. Again, anyone who's played with C is probably relatively familiar with arrays. One difference between, say, a C array and a Rust array is that Rust arrays of different lengths are classed as different types. And so they're not just a pointer to some start, offset 0. A 4-byte, you know, or like an array of 4 integers is different from the type point of view of an array of 40 integers. And so you can't use them in the same places. I've mentioned references once or twice before. It comes with this kind of ampersand syntax. They are implemented as pointers, but at the type level, the compiler will guard against mutable access, and therefore, yeah, I'd like the term read-only versus read-write rather than immutable and mutable. Okay, so cool. We have got through, we've got a toolbox now, we've got primitives, we've got collections of things, we have the ability to create compound data. So let's kind of put that to use.
Just that I'd note, if anyone's trying to do this on Mac, I found it when it first opens, it doesn't have anything on the logo display, but if you full screen the window, it seems to appear.
Oh, right. Okay, so you're saying the turtle thing doesn't seem to,
Like a black white window that's bigger than the display, and you can't see anything. If you hit full screen, it seems to make it work. So if anyone else is trying to do it on Mac, then that might help.
we should file a bug.
We've already had one person at the back that crashed his graphics card driver.
Oh, God.
It's making the window size.
Have you also had the same with the graphics card crash?
I've got different signals. I was running the WSL on Windows, and it didn't work. So I tried to install it under Windows natively.
Oh, well, I really apologize for using a library that,
Should know better than to expect Linux graphics to work with Linux.
that's breaking for people.
Keep Pathfinder from next door scaring all the GPUs.
That's right. I feel really upset about that. So you're just going to have to trust me that this works by watching. Okay, now we're going to introduce, I've introduced a lot here. We haven't added any imports except for turtle, which we had previously. I'll try to make that even larger.
Which one are we in?
We're in interpreter 1. All right. Okay, so let's kind of work through. Do you remember how I mentioned with the fractal that every iteration made things more and more complex? We need to define an integer that provides how many iterations we're going to go through. There's another keyword that we can apply here as well called const for anyone that would like to. So the difference between a const and an int is that const will be copied. What is the difference? Does anyone feel like? Yeah, so we, apart from the fact that everything was already immutable anyway, const is just going to provide, it will copy things locally around rather than pushing things to the stack. It's, I can't even, sorry, my mind's kind of gone blank as to.
The left makes a stack frame for it, whereas the const is going to copy it everywhere it's used.
Yeah, right, okay. So at compile time, the let will create it'll allocate to the stack inside the scope that it is, inside the stack frame. Whereas consts are it's going to replicate that constant everywhere it's used. So, because the compiler knows by default, by design, that it's never going to change, whereas it can't actually make that guarantee.
So it's almost like a C macro? Like a hash define?
No, not quite.
Yeah, it's not quite a macro, but
It's more of a global variable that you can't modify.
They're not copies, they're referenced.
It never falls out of scope, no. What was that?
Global variables in C are referenced, not copied.
It's probably a bit more complicated than just this. So there's a bit that because of the type system, Rust can be more aggressive with the compiler in doing things where C can't, because C, the gloves come off everywhere you've gone with C. And that's why you end up with getting references everywhere, because even though it's not a good idea, you can go and mutate that, whereas with the const, it So there are other optimizations that can be made when it is const. So it's not quite a macro, but it's also not quite a, so it's not quite a define, but it's also not quite a global either.
That clears everything up.
Yeah, right. So if I can kind of maybe push back, or not push back, but kind of like spill out my own brain about it. Const is going to provide the compiler with more ability to optimize the exact use in wherever it's used. That's my understanding. Whereas it's going to take an assignment binding. It's going to always do the same thing. Now, you can start to play. So we've only got, if we go down here, we've only got a couple of instructions defined. We've got forwards, left, and right. But presumably, we can create a more, so this will create, this is our initial state. And if we felt like it, we could muck around and say, whenever we match F, we can change what the turtle is doing. So I'll just kind of go back. So some things about Rust. String literals are not uppercase string types. They are the difference between, well, a good analogy would be an array versus a vector that we've just seen. This type here of the string literal is much more like an array, whereas a string is much more like the vector. It has more operations. You know, it's sort of more convenient to use, and you can't expand it. You can change things in these guys. You know, you can mutate a single value, but you can't expand it. We've already touched on the fact that a character is not a string, but we've got something else, which is a byte literal. A byte of a single character is a U8 value, so it's actually, you know, just the number, but we're taking the ASCII value. This into, I'll just break this apart. So here I've got this kind of weird syntax. I can either create a string by calling string double colon from brackets, da 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 da. Otherwise, I could ask Rust to convert between one type and another. I'm just going to call this rewrite. And if I provide the type parameter, it will probably know how to do that conversion because it's been given this type information. In here, what we're pushing to our rules vector is a tuple up here of a number and a string. And you can see that our type has been echoed back to us. Now, this is a pretty ugly way to look at left angle bracket, da da da. We can actually define a type alias as well. It's another kind of fancy feature. Well, not even fancy feature. This is purely kind of syntactic sugar for us. And if you've got any creative, did anyone create any creative squares? Does anyone want to give me another rule? Put some extra accent. Yeah, sure. We can. So I can. I'll go through this iteration because there are a couple of extra things that you probably wouldn't have encountered. So in every iteration of our loop, we take the pattern, our initial state, which we originally called axiom. It's the terminology that's used in the book, but we're calling pattern here. We ask for an iterator of bytes. And so for every, it's not a great variable name, for every P in pattern, and for every rule that we have in our list of rules, we ask whether or not our matching byte matches the P that we've got. Does that make sense? Probably not. Anyway, we can, so once we've found an F in our, so we're iterating through this one up here, and we're also iterating through our rules, and we're looking for Fs. So whenever we find an F, we replace it with this push stir with these 5 characters into next pattern. Once we've hit a rule, our loop then stops. Rust provides a really cool feature, structured go-tos, maybe, of being able to break out of loops at arbitrary depth by providing a label for every loop that we want. It kind of reduces a little bit of, so they will ask, it will bump out of this if and this for, and it'll go all the way up to the top level. And I find that, removes a lot of ambiguity from like break statements that are nested in places, and we avoid like go to fail and so forth.
A single quote, really?
What's that?
A single quote, though, really is the character.
Yeah, right. Like, it's ugly, but it's practical. 30 minutes to go. That's good. Yeah, it's kind of, look at, like, I feel like Rust is ugly in the same way, but it's kind of an appreciation for it in the same way like I have an appreciation for an I-beam. Like, it's, it's, I like that it's, I would rather have a very strong I-beam holding up my building than some kind of weak, artistic, kind of creative thing that is untested. I don't know, is that analogy, I don't know.
That's a great analogy, and I'm just going to quote that.
I don't know. I've been too kind of dunked into the Rust world that I actually, like I've taken the ugliness and the arbitrariness of some of the stuff that it does, and just said, that I kind of like it. And I'm a big advocate for the language, and the benefits that you get from using a system that has a strong type system prevents you from being able to make errors like missing else statements and so forth, just makes it so much better for me as a stupid programmer, and it enables me to explore computing in a way that I've never done before, that I think it kind of outweighs the problem that an I-beam is ugly, but it's strong, so good. Right, so we've kind of gone through. I would like to ask if anyone has any questions.
Is there a character type if your string is not ASCII?
Is there a character type if your string is not ASCII? That's great. Yeah, right. So, okay. So there is a character type with just single brackets. It is guaranteed at compile time to be UTF-32. There are some other exceptions, though, that I will get to very, very shortly. No, characters are 4 bytes. The character type is 4 bytes, and it just happens to be UTF-32.
How do you iterate on those? Is it just dot character or something?
Dot cars. So here we go. So whenever we encounter the stir type, you almost always take a reference to it and play with it via a reference. It's more lightweight than string, but it has less functionality available to you as a programmer. So there are 4 types of literal strings which, in fact, there's also raw strings that enable multi-line stuff, but I'm sure you can read the docs. A single character is a UTF-32. If we create, we can have a single byte. So these two look very similar in source code, but are very, very different to the type system. Likewise, here we have an array of length 1 and just a single scalar value. Oh, sorry, does that term scary? Or, yeah, but now we get to the rest of the world. Not everything is guaranteed to be UTF-8. So we've kind of got some escape hatches in the standard library. One of them is a C string and C stir. So this effectively is a C string available to you as a Rust programmer. Now, the language will push you towards taking that as ugly input data, validating the contents, converting it to something that's type safe, and then continuing on. There's also a operating system native string type. So for example, Windows will have its own version of what it believes a string is versus Unix and so forth. And they're available to you via the standard library. One thing about Rust that I found really confusing, especially as a beginner, is that the definition of data and the methods that it implements are separated. So here again, we have this kind of other thing. We've got like some agent on our brand new game. If I compile this, I'll just create an agent. Where should it be? 5, 5. Okay, which direction should it head? One thing I've wanted to do, but I've never been able to figure out how to do, is create a type that, say, is a floating point number, but is constrained, say, between 0 and 360. I think, some other languages can do that, and Rust cannot, as far as I believe. So we've got this kind of agent thing, and we can turn it to, turn it around. It should wrap, but it doesn't. Oh, goodness me. How do we fix this? Does anyone want to guess? So, okay, we'll start by saying, buddy, we want to mutate it. So is that going to help? Actually, yes, it does. So again, Rust is going to kind of be on our side in a really annoying way. Did we just look through twos? No, we didn't. Trust your talk. Your slides are there for a reason. So I'm just going to open up the other project. It's probably going to ask me if I want it to open it at the same window. My code gets progressively uglier as these examples become more in depth. Here are some things that we've changed. We've added some parameters to our code. I'll just view presentation. Oh, wrong way. They're all pretty simple. We've changed the rule. So now actually we start, our very initial pattern is an X. We still have our forward rule, and all our forward rule does is expand the member, like it just doubles the length of whatever thing that we've got. And I've added some additional I've added a stack, like our position. So surprisingly, like point and location, sorry, our location in Cartesian space, as well as our heading. So very similar to what we just had. I've also added this lowercase. By convention in the LSystem notation, lowercase letters are moves that do have no pen, but we don't actually make use of that in our code, so we could probably comment that out. Our left bracket or left square bracket saves our position to the stack, and so at that point, we take our current position and our current heading, and we append it or push it to our stack variable. And then on the right square bracket, we kind of need to go through a little bit of magic. Firstly, we pop the stack, so we take off the most recent value. We need this unwrap thing, which I can explain. I'm actually going to punt until I've done one more, and I'll explain. Basically, this is saying that Rust is concerned that the length of the stack might be 0. So it's possible, from the type system's point of view, this call will fail. And I'm saying, no, Rust. It will not fail. So it's going to give me a little container object that it calls a result, and I'm going to unwrap that and get out the value. And if I'm wrong, the program will crash. So have fun with putting a bracket right there. This is not idiomatic Rust code. Right? This is kind of one of those, it's there, but while you're starting, it can be super handy to just throw an unwrap. Would you kind of be, William's nodding? Josh, you're nodding? Yeah.
You can also use expect and have a comment in there as well, so you know which part of the code actually is what blew up instead of just, something blew up.
Or just use unwrap or default to
Yeah.
same value back.
There are actually about a dozen methods that you can do. You can say, look, the stack's empty, or default, or else, I believe it is. And we could say, actually, if the stack's empty, just put me back to position 0, or whatever we want. But right now, we're just going to blow up. We take the pen off the paper, move to where we were on the stack, set our heading to that old direction, and then we carry on. This code here is what created the tree. And let's do it again. So hopefully I don't crash my computer. My IDE is actually a pretty memory or resource intensive thing. I'm surprised though that it's not making any progress. That's not a useful sign. And also my mouse cursor is also surprisingly jumpy. Oh, and I'm starting to take off. So, good. Okay, well, we're just gonna leave there. I think I'm gonna abort. Oh, and I can't. So, hard reset time. Hopefully they can kind of carry on. How about, does anyone have any questions? How about we talk about results? So there are two enums that are ridiculously useful for Rust programmers. Result and option. Result provides you as a library writer, and thus you as an application developer, the opportunity to be informed that something went wrong that you can probably recover from. Or at least I'm going to give you the opportunity to recover without blowing up. So in particular with I/O, almost every single method will return a result. And as we've just described, a result is actually kind of this little package of an OK or an error. Like there's just two sides to the enum, and inside OK is your value, and inside the error is a custom error type. we're still not moving. Uh-oh. And I'm like fully locked now. So this is awesome. Oh. Uh-oh. Alt F4 is still, I don't even know, I'll try. Damn it. So. Yeah, right. Yeah, well, yeah. It's like, I'll just SSH into my. What's that?
Maybe memory's not the limit.
Yeah, I don't think it will. Yeah. Well, we can all talk about the scheduler another day. Yeah, right. So yeah, rewrite the scheduler in Rust, hopefully. Anyway, so results. Results provide you an opportunity to recover from errors. They do it in a type-safe way. Whenever you deal with I/O that could fail, you'll always get back a result. It's so common that they added syntax for effectively calling that unwrap command. It's just a question mark. And what the question mark will do is propagate up the error in the call stack. So for example, if you have multiple functions, every single one will return a result, and it will basically cascade back up and allow you to handle the result at a time that suits you and hopefully the user. Options are similar but different. They feel very, very similar, especially if you're brand new to the language. But an option is semantically quite different. If you have an optional parameter, something that may or may not be present, that's different than something that might or might be wrong or might blow up in your face. And so you'll find option being returned when a vector might not have something to give you, when it's empty. They have very similar methods, like unwrap. Like I assert that it is there. Oh, I'm really upset that this is not working. Do you mind if I just take a quick break to talk to the AV guys about whether or not, can I restart my computer? Yeah, absolutely. All right, okay, cool. I'm just gonna do that. Could you guys like swap off? Yeah, no, I'm just good on the camera. Oh, sweet, okay, cool. That's fine. Right, so the next question, or the next part of the Rust, actually we've got probably in the order of, well, we've got some time to answer any questions. Who has found something at Rust that they've struggled with? Who has got a specific question about a part of Rust that they would like maybe, does anyone have any questions that they would like to ask about the language or about the community or so forth? You just shout out and I'll try to repeat them at the back.
Do people, when you have the immutable types, sorry, I've got a microphone. Does Rust do the sort of thing where you take a copy of it and return a modified copy? Is that a thing in Rust, or does it just mean you just don't modify it and you just leave it be?
Right. So my understanding of the question, it's like, say I've got something, and I know that it's immutable, but actually I still want to change something.
Yeah. Does it do that functional approach that people use?
Yeah, you can. So there's two ways. There are two traits. So everything in Rust, all behavior of data, is implemented within traits. And there are two traits that are going to become important if you dig deeper. One is copy. The copy trait will implicitly duplicate values if you break Rust's normal rules. So Rust's normal rule is that there can only be one owner, and primitives are basically able to break the rule because primitives are kind of safe to duplicate whenever you want. But that doesn't help if you've got a custom type or anything more complex than a number. For that, you have the clone trait available to you. The clone trait is defined by a single method, clone, and effectively you can opt in to duplicating the value and then mutating it? So it's a long way to answer yes.
Clone heap, or you can choose?
You can opt in if you've, you define what clone means. Yeah.
If you write clone, like he did earlier, that'll do a deep copy on anytime.
Yeah. Yes. Typically, you should consider clone an expensive operation.
Sorry, so just to add to that question, there's no sort of accelerated, high performance data structure that you can use to reduce the cost of that copy? Like, so you actually, copy on change rather than, or is there?
Yeah, feel free. Have we got the mic? Thank you. Yeah. I'm just about
Okay,
ready.
so part of the value of Rust is that because of the nature of mutable and immutable, because you can share those things immutably, not just between functions, but between threads, you now have a way that you may not need to actually trigger clone in the first place, provided that data is not going to be mutated. So you may not need the clone at all. So generally, you would pass, say, a reference that is immutable, and then that can also accelerate. You can use that in many threads, or you could use that in various other ways, and that enables other further compiler optimizations. So you may not need to clone in the first place. So that's one of the things that the reference system enables you to do in terms of high performance without having to worry about, say, memory modeling and thread safety. Like, it's completely taken care of in the compiler. So that, I hope that answers that question.
Yeah, thanks very much. I should have done the code talk thing, hopefully. So my screen is now back, AV team. Thanks, guys. So there's one, I've mentioned this word traits a little bit, and I just wanted to explain to them, explain to everyone what that actually is. A trait is a set of function definitions. It is kind of, if you're from the C world, like, in a sense, kind of a little bit like a header file. We have our prototypes, and we invite types to opt in to implementing the trait. The term trait, though, is odd. So just think of them as abstract baked classes. And then a lot of the confusion about, well, what is a trait? Like, does that mean it smells nice? Like, is it strong? Like, I don't know. I found it hard. So it doesn't mean personality. I'm going to come back to that, and we're going to try with our last few minutes to skip. I'm going to try to talk through some Rust code. This here is a server. We've got a main function. We've basically got a couple of imports. They look a bit gross. That's okay. That's our IBM. We bring in this thing called open options, which is a struct that knows how to provide parameters. The reason why this is important is that we want to open a file later on. We bring in a set of traits from the prelude. So in order for us to be able to call methods, we need the traits to be in local scope. And also we've got a couple of structs, a couple of types here from different parts of the standard library. I'm going to talk about what we do once we receive a connection. So this open options thing enables us to do something like we would with keyword arguments in like a Python or a JavaScript. There are no keyword arguments in any Rust methods. So instead, they've got this notion, well, it's a Javaism, I believe, it came from, called the builder pattern. The builder pattern is very common, where you will have some type that have methods that mutate itself, which then knows how to create the thing that you actually wanted to create. So you call methods that are parameters that it uses to build the thing that you're interested in. So open options knows how to create files with different types of permissions, whereas just calling like file open would by default create you like a read-only file, I think, and that's not what we want, because what we're trying to do is open this file and then write out, and it may not exist at the time that we call the function, and then we'd like to be able to send what the user has given the server and write it to disk. Notice here that we have a couple of these silly question marks. They avoid us. In fact, they're slightly more powerful than the just calling unwrapped, because they do propagate the error back up to main. So if there was a problem here, say for example, the disk was full and it couldn't write a message to disk, handle client would return an error which would then be intercepted by main. Rust provides the ability for types to opt into conversion. So it's kind of feels a bit magical that you can just provide a string to a method that actually wants something much more structured, because kind of the Rust way is to not like strings, but instead ask for an actual struct that has a domain name and an address. And if you look into the details of how this happens, there's an implementation of the from trait, which enables strings to kind of say, oh, this is how you convert me into a IP4 address. And so you can kind of create these lightweight parsers for different types, because a TCP listener really wants an IP address. It doesn't actually know what to do with any given generic string. This will never happen, but when we get to the end of the function, because we've got this result type, we also need to present it with OK. This OK with this unit value, which, as we've touched on before, could look like that. Okay, thus ends the tutorial, I believe. Thank you very much for attending. Oh, we've got 2 minutes. I'm more than happy to answer any questions, or at least field them. One at the back. Ah, right, so there was a question mark, oh sorry, an exclamation mark somewhere, and I'm going to, I know exactly what it is. Ah, right, here, right. Actually, I intentionally decided to not talk about macros because I didn't want to confuse people, but I decided to put one in anyway. Rust has a function like macro syntax denoted by an exclamation mark. It's from a user point of, or like you as a programmer right now learning the language, it's just a function. It's not actually a function, but right. There are two macros that are useful, actually 3. One is write line, the other is print line. I can't get to it. And the last one is ePrint line, which prints to standard out. So here I have write line, standard error, sorry, that takes something that can accept something to be written. So I've got the file, which can accept. There's also print line, which has this kind of format mini language. We have a reference to the output, and that also, actually, that might. And so this one, print line will go to standard out. ePrint line goes to standard error. Okay. Oh, this isn't actually code. This is markdown. This might get unhappy. Yeah, it's saying, look, hey man, look, there's a macro called ePrintLine. Is that what you meant?
Yeah, so macros and functions are different namespaces.
Yeah. So what they're saying there is that just for the AV, they're different namespaces, and so.
One last question.
What does the ampersand mute on the stream.read2string in front of output, what is that?
Right, okay, so we have this output thing. We'll think about it from what we want to be able to do is pass a reference to read to string, but the owner stays in the same place, but it can send references elsewhere. So read to string is borrowing output in a mutable fashion. Basically, we're giving a pointer to read to string and allowing read to string to mutate that pointer. In C, we would need to ensure that we didn't touch the output buffer within handle client. We need to make sure that once we've given the pointer to read to string, that we don't touch it anymore. Otherwise, we're going to kill ourselves. Yeah.
We'll leave it at that. Can everyone put their hands together and thank Tim for the great presentation?